In this lesson, we're going to look at solving problems involving trigonometry, sometimes in 3 dimensions as well, which just means that you have to be able to visualize the problem in 3 dimensions. The actual triangles are still something that are presented in 2 dimensions. So anyway, 2 and 3-dimensional problems involving triangles can be solved using some combination of the following approaches. We can use trig ratios if we have a right triangle. We can use the Pythagorean theorem also if we have a right triangle. We can use the sine law if we have a non-right triangle where we know the side across from the angle. Remember, the sine law is what we use. The sine law is given as A over sine A equals B over sine B equals C over sine C. We don't have to use all the parts, but remember that we can use any 2 of those parts where little a, b, and c are the side lengths and little big a, b, and c are the angles. So for angle A, B, C like this would be side little a, this would be side little b, and side little c. They're the ones that are across from the angles. So as long as I know an angle across from a side, then I can use the sine law. And the cosine law is also for non-right triangles. Remember, depending on what we're looking for, if I wanted to find side C, again, refer to this triangle here. Say I wanted to find side C. If I know 2 sides with an angle in between, then I can find out the other side. So C squared equals A squared plus B squared minus 2AB cos of C, and that's the big angle C. Often it's necessary to solve problems in multiple steps. So what we're going to do is we're going to use the trig ratios or the Pythagorean theorem or the sine law or the cosine law, whatever presents itself, to solve what we can solve. And then we're going to just keep going until we get to what we're actually asked to solve. An accurate sketch or sketches is, of course, essential. Whenever we're doing trigonometry, it's really important that we have proper sketches to help us see what's what. So for this first example, determine the value of x to the nearest tenth of a meter. So we want to find x. In order to find x, I've got the angle here, but I would need one other side being a right triangle. I could use trigonometry, but I don't have a side. So probably this would be the side here that I would need to know. So I could call that y or whatever. But I can't find that. I don't have that, so I can't find x. So maybe I could work backwards and say, okay, well, let's find y. Well, here's another right triangle here. And what do I know about that triangle? Well, I know that if this is 90 degrees here and this is 45 degrees, then I do know this angle has also got to be 45 degrees. But I'm missing, if I want to find that what I've called side y, I would need to still know either this side or this side. I need to know another side. So I'm still missing something. And the logical thing to find would be this side here. Maybe I could call that z. Okay, so now I know I've got to find that side. And do I have enough information to find that within this triangle here? And it's not a right triangle, but it does have a lot of information. I know this side length and this angle across from it. I know this angle across from Z. So yes, I could set up the sine law to find the side length that I've called Z. And then once I know Z, I could find y. And once I know y, I could find x. So that's the idea behind this problem. So Z, using the sine law, little z, is going to be over sine 80, because these things always go in sine 80. Can't seem to write what I want to write. I keep saying one thing and writing something else. There we go, sine 80. Because these two are across from each other, right? We set up angles and sides in pairs when we're working with the sine law. So z over sine 80 is going to be equal to 3.2, the other side length, over sine 45. And then remember, I can cross multiply, although when I'm cross multiplying with fractions, And if I want to get z by itself, the easiest thing to do is, I know that this sine 80 is just going to end up at the top of this other fraction. So it's going to end up being z is equal to 3.2 times sine 80. And then I'll divide that by sine 45. And when I do that, I can type that all in my calculator at once. So 3.2 times the sine of 80 degrees, and then I can divide that by the sine of 45 degrees. And I got 4.46 to 2 decimal places. Actually, maybe I'll go to 3 decimal places. I don't want to round too much too early. So I'm going to go 4.457. Let's round to 3 decimal places for now. 4.457 meters. And the reason it's meters is because this side length was in meters, so z has to be in meters as well. So z is 4.457 meters. All right, maybe I'll even add that to the sketch, 4.457. Now I'm set up so that I can actually solve for y, because I know the hypotenuse of that triangle right there that I just outlined. So I can find y, or at least I can set up the trig ratio. So if I do that first, the next thing I'm going to do is set up the trig ratio. I know that sine 45 is equal to, y is the adjacent side, isn't it? And z is the hypotenuse of that triangle. So it's going to be not sine, my mistake. I jumped the gun on that. It's going to be cosine because it's adjacent over hypotenuse. So cos 45 is going to be y over 4.457. And then if I rearrange to isolate y, I get 4.457 times cos 45, and that'll give me what y is. And one thing I can do, even though I wrote down 3 decimal places, you can see there's a lot more decimal places here. I can keep that and just, I'll say, what was it I wanted? I wanted that number times cos 45. So I can say answer. Usually there's an option to grab your answer somewhere. For me, it's on the keypad beside the decimal. You can see ANS. So I can take my previous answer and multiply that times cos 45, and so it just keeps all the decimal places for me. That's usually an option. So now my new answer is 3.151 if I round to 2 decimal places. So y equals 3.151, and again that's in meters for the same reason that we started off with meters for our first side length. It's going to stay in those same units. So that's my answer for y, 3.151 meters. And now finally I've got enough information that I can find out what x is. This is my third step. From this 70 degrees, y is my opposite side, so this y becomes opposite side. X is my hypotenuse from that one. And so for opposite and hypotenuse, I've got sine 70 degrees equals y, which is 3.151 over x. And then I can solve this for x. So if I multiply both sides by x, I have x sine 70 equals 3.151. I could divide both sides by sine 70, so 3.151 divided by sine 70. And again, I can just take my previous answer and say divided by sine 70, and 3.3536, etc. Now would be a good time to round it. So maybe 3.4 or something like that. Does it say nearest tenth? Yeah. So x, now that I'm done, I'll round it to 3.4 meters. And there's my final answer. So a multi-step problem. And so you have to solve what you can and just work your way towards what you don't know. Here's another one. I think this is supposed to represent a 3-dimensional sketch, although it doesn't really matter whether it does or not. I guess the only thing that makes me think it's supposed to be three-dimensional sketch is this angle here looks like it's a lot more than 92 degrees. So if this was three-dimensional and this triangle here was lying on a horizontal surface coming out of the page towards us, then that would make sense. But it doesn't really matter. It's just another one of those work your way around until you get to what you need to get to type questions. So I'm supposed to find x in this case, but again, I know an angle, 51 degrees, but I don't know any sides. What you're looking for is sides that are shared. So the shared side in this case would be this one down here at the bottom. So if I call that y again, this would be a situation where I could solve for y. So what do I know? I know this side across from this angle, and I want to find the side across from this angle. So again, this is set up as a sine law type question. So I can do y over sine 67 equals 3.1 over sine 92. And again, I could cross multiply, but I know when I do that, I'm going to end up with 3.1 times sine 67 on the top over sine 92. So I always just sort of jump straight to that to save myself the bother of going through the process of cross multiplying, since I know what the end result is going to be. So if I type that into my calculator, then I'll get what y is equal to. So 3.1 times sine 67 divided by sine 92. And I got 2.855. Again, I'll round it to 3 decimal places for now because I don't want to round too early. 2.855. And the units are going to be nothing. There's no units given, so I won't do units for this one. So that's what y is. Now that I know what y is, that it's 2.855, then I can use trigonometry to find out what x is. From the angle of 51 degrees, I know that y is my adjacent side and x is my my opposite side, so I can do tangent for opposite over adjacent. So tan 51 is going to equal x over 2.855. And again, I can rearrange to isolate x. So if I multiply both sides by 2.855, then I'll have x isolated. And again, I can just take my answer from before. So answer times tan, what was it? Tan 51, it appears. So 2.855 times tan 51 is 3.5 to 1 decimal place. So x equals 3.5, and again, by doing multi-steps, I was able to get what I was looking for. So you just have to sort of hunt around a bit sometimes. Well, Janvier and Xavier, I don't know if I'm saying that right or not, but hopefully I'm not insulting anybody if I'm pronouncing it wrong, were flying a hot air balloon from Able to Brownsville. They calculated the straight line distance between the two towns. From an altitude of 250 meters, they simultaneously measured the angle of depression to Able as 4 degrees and to Brownsville as 5 degrees. They measured the angle between the lines of sight to the two towns as 77 degrees. What is the distance between Able and Brownsville to the nearest meter? So it's really essential that we draw a picture when we have questions to deal with like this. So let's put A for Able here and B for Brownsville. I imagine that's why those names were chosen, to make A and B anyway. And Xavier and Janvier were flying a hot air balloon, and from an altitude of 250 meters, they simultaneously measured the angle of depression to Able as 4 degrees, Brownsville as 5 degrees. They measured the angle between the lines of sight to the two towns as 77 degrees. Okay, So this is a three-dimensional problem. So I can put, let's say, let's call the hot air balloon C, the spot where the hot air balloon is as C. So let's put it over here. The problem is that this is not two dimensions. So imagine the ground, if I was to draw a straight line down to the ground, maybe this would be the ground over here, and they're not actually between the two towns at all. So it's not just a matter of drawing a triangle like this. It's going to be something more where there's a bunch of triangles going on. So if that's the distance to the ground, or a straight line to the ground, I could make a right triangle from this balloon at C. It doesn't look like a right triangle because I'm trying to represent three dimensions on a flat screen, a flat page, right? But if you use your imagination, you know that the dotted line represents a vertical line straight down to the ground. This line here is a horizontal line. It just is represented to not look horizontal because of the three dimensions. And then the other line would be the hypotenuse of my right triangle. So we got the same thing going for each of these two triangles. So there's another one where they got this is their line of sight down to the town of Abel. This line here is the direct distance from wherever, their balloon is straight below their balloon to the town, and this also would be a right triangle. And so, let's see, they have an altitude of 250 meters. So let's do that as kilometers, because that's probably a better unit for distance between towns. So if I change 250 meters to 0.25 kilometers, that would be the length of that dotted line, their height. We also know that they simultaneously measured the angle of depression as 4 degrees to Abel and 5 degrees to Brownsville. So again, let's imagine, we have to try to get good at visualizing. So let's imagine a straight line. If they look out straight towards Abel, but not downwards, so this is supposed to be on the same plane as where the hot air balloon is, then this angle that they're looking down at an angle of 4 degrees. So that's 4 degrees in here. The reason that's useful is because this is another right triangle here between that dotted line and this dotted line. So if that's a right triangle at 90 degrees, that means that this angle in here has to be 90 minus 4. So that must be an 86 degree triangle or angle right there. Also, that means that this must be 4 degrees here, whether you want to just add up all your angles in that right triangle to make them 180, or whether you want to think about what you know from grade 9, the Z pattern for parallel lines, for transversals. Either way, this is 4 degrees here. And likewise, this would be 5 degrees, again, following the same pattern. It's 5 degrees in here, which means that would be 85, very hard to, I didn't make my diagram big enough, but that'd be 85 degrees in here. And that means that the other angle down at the bottom would be 5 degrees. Finally, what else do we know? We know that there's a 77 degree angle between the lines of sight of the two towns. Well, this is a line of sight from the hot air balloon to Abel. This is a line of sight from the hot air balloon to Brownsville. So it's going to be very messy here, but let me try. Between these two lines that I've done in green, that's 77 degrees. That's all the information we have. What's the distance between Abel and Brownsville? So now, after all that, we want to find the distance between these two towns. All right, so if I want to find the distance between these two towns, I need to know a couple other side lengths. And maybe, what side lengths do I want to know? I need to know, well, I could find this side length, and I could find this side length. That's not that hard to calculate. I would also need to know another angle. If that's 77 degrees, actually, you know what? I'm not going to find out those ones. I'm just thinking this through on the fly here. Oops, didn't mean to erase all that. Rather than finding those two, I would think that I would want to find these two, and then I could use the 77 degrees to find out the distance between A and B. So let's take this one step at a time. Okay, so here, let's start with this triangle here, this right triangle here that I just outlined in yellow. Let me draw it again over here. What we know about it. We got 4 degrees down in this. This is not to scale out. We got 4 degrees down there. Obviously, it's going to be much more stretched out. 86 degrees up here. We know that this is 0.25. I want to find, let's call this x here. So I'll call that x and I'll put that there. So I want to find the hypotenuse that I'm calling x. So if I do that, let's maybe go from this side here, the 4 degrees. That makes the 0.25 the opposite side. So sine of 4 degrees is equal to opposite, so 0.25 over x. If I rearrange this, multiply both sides by x, divide both sides by sine 4 degrees, then I've got, well, whatever 0.25 divided by sine 4 is. Let's see. 0.25 divided by sine 4 equals 3.584. 584, and that would be in kilometers because the 0.25 is in kilometers. Okay, so that's that triangle I did in yellow. Let's outline the other right triangle in green. So this is another right triangle. We're going to outline that one in green. Maybe I'll do that one down here. So it was like this. And let's just match it up color-wise. So we had a right angle here. We had this side is 2.25 kilometers. We knew that this was 5 degrees down here. And we want to find, let's call this side here y. All right, so I found x. I want to find y. And so if I call that y, again, that's the hypotenuse. So again, I'd use the exact same setup. So I could go sine, except this time it's 5 degrees, would be 0.25 over y. When I rearrange to isolate y, I'm going to have 0.25 over sine 5 degrees. And I can actually just change this 4 to a 5 since I've still got it on my calculator. I got 2.868. 868 kilometers. Okay, so now I know x and y. Why do I want to know that? Because they form, there's so many triangles going on here. They form, let's use a dark color. They form a triangle, a non-right triangle here, where one side length is y, another side length is x, and the angle in the one of the corners, the angle between x and y, is 77 degrees. And I want to find, let's call this z. Z is actually the answer to the problem. I need to find what z is. This is a cosine law problem because I want to find the missing side length when I've got no two sides in the angle between them. So using the cosine law, z squared equals, using the variables I've talked about, x squared plus y squared minus 2 times x times y times cos, well, I didn't even have a label for that one, cos c. Anyway, let's call it 77 degrees. Let's fill in the blanks. So x was 3.584 squared plus 2.868, that was y squared, minus 2 times 3.584 times 2.868. Again, I'm trying to keep my decimal places for as long as possible, at least enough of them, and I'll round at the end. So 3.584 squared, I'm going to have to go back and forth because I'm not going to remember all this. 3.584 squared plus 2.868 squared 2.868 squared minus 2 times 3.584 times 2.868 times cosine of 77 degrees. Okay, 16.4459, etc. So 16.446. That's what z squared is. But remember, whenever we do the cosine law, just like with the Pythagorean theorem, the last step is to take the square root of both sides. So I'll take the square root of that answer. Square root answer 4.055. Let's round to 1 decimal place again. 4.1 kilometers. So it turns out the distance between Abel and Brownsville is 4.1 kilometers. So the hardest part for a question like this is visualizing it. And even when I drew a sketch, it's hard to visualize. It's hard to visualize three-dimensional things in 2 dimensions. I guess what I never did over here, which for this last one, which I probably could have done, was drawn a sketch for that one as well. Because what I knew from that red one was I knew what x was, which was 3.584, and I knew what y was, which was 2.868. And I knew that this angle here between them was 77, and I wanted to find this one. I just didn't draw my sketch at first, which I should do. So always draw a good sketch. Take your time and be sure